In this video, I want to further our discussion of where subgroups come from. So the reference for this video is section 2.4 of Dummett and Foote. And we've already talked about cyclic groups. So we know that for any x in G, we have the cyclic subgroup generated by x is a subgroup of G. But what else? Like, what about subgroups that are not cyclic? How do we find those? And I'm going to start with a fact about the intersection of subgroups. So let's let A be a non-empty collection of subgroups of G. It can be finite, it can be infinite, it doesn't matter. The intersection of all the members of A, the intersection of all those subgroups, is also a subgroup of G. So one way to get subgroups is to take subgroups we already have and intersect them together. Okay, so how do you prove that? The subgroup criterion. It's a very convenient way to prove that something is a subgroup. So let's name this intersection of all subgroups in this set A. Let's call that K. Well, every one of these subgroups is a subgroup. So in particular, they all contain the identity of G. So that identity of G has to be in the intersection. So all we have to do is prove that if A and B are in K, then A times B inverse is in K as well. Well, if A and B are in K, then they're in every single one of these subgroups H. So A, B are both in H for all of these subgroups. That means that A times B inverse is also in H. Because if you have a subgroup H that has A and B, it also has AB inverse, because it's a subgroup. But that means that AB inverse is in H for every subgroup in this index set A. So it's in the intersection. And that's it. So this gets a name now. If you take any subset of G, it could be a subgroup, doesn't have to be, could be anything. We're going to use this angle bracket notation to denote the intersection of all of the subgroups that contain this set A. So the intersection of all of these subgroups that contain A, well, that's some set of subgroups. So this intersection itself is a subgroup. So that gets a name. That's called the subgroup of G generated by A. So we just talked about cyclic groups and how the cyclic subgroup generated by X is the set of all the things you can write as X to some integer power n. So maybe it feels weird at first to call this the subgroup of G generated by A. I'm going to explain that in a minute. This is the intersection of all subgroups containing the set A. And we're going to see that it's equivalent to a different description that maybe matches up better with what you would think of as the subgroup of G generated by A. So I'm going to pause and erase and show you this other way to think about this intersection of all subgroups containing A. The next thing I want to do is give you another way to think about this subgroup generated by A. So we saw that this is the intersection of all the subgroups containing this set A. Let's define A bar to be the set of all words of finite length written using the elements of A and their inverses. So what does that mean, words of finite length? It means you write down strings of like A1 times A2 times A7 times A9 times A3 inverse times A5 inverse, where you run through all of those elements of your set A. So more precisely, A bar is the set of all things that can be written as A1 to the epsilon 1, A2 to the epsilon 2, up to AN to the epsilon n. N is just a non-negative integer. This includes the empty product, which gives you the identity. And each epsilon I is either 1 or -1. So you're either taking A1 to the 1 or A1 to the -1, which is A1 inverse. Oh, yeah, I should say, what else? These AIs are all elements of A. Okay, and this looks closer to the construction of what a cyclic subgroup is. All the things that you can write as x times x times x times x times x, sum n times, or x inverse times x inverse times x inverse, some positive number of times. So the proposition is that these two subgroups are the same. So I don't want to give a full proof of this. What's the idea? Well, first we have to show that this A bar actually is a subgroup of G, no matter what A is. And the way to do that is with the subgroup criterion. So that's pretty straightforward, so I'm not going to do the details. It's a good exercise. And then we also want to show inclusion each way. So once we know that A bar is a subgroup of G, it clearly contains A, and we know by definition that this subgroup generated by A is the intersection of all the subgroups containing A. So in particular, it's in the intersection of A bar and a bunch of other stuff, so it's contained in A bar. The inclusion the other way takes a little bit more work, and I'll let you think about it as an exercise, or you can look it up in section 2.4 of Dumb Input. Okay, let me introduce a couple more new pieces of language, and then I'll show you some examples. First, this isn't going to be relevant for a little while, but we have the tools to understand this definition, so I want to give it to you now. A subgroup is called finitely generated if it can be written as the subgroup generated by A for some finite set A. So you can think about this, but I hope that it's clear that any finite subgroup is finitely generated. You just take the whole subgroup and take the subgroup generated by that subgroup. So if that subgroup is finite, it's automatically finitely generated, but there are lots of infinite subgroups that are finitely generated. Like Z, for example, Z plus is cyclic. The subgroup of Z generated by 1 is all of Z. It's generated by that one single element, but it's infinite. So there are finitely generated subgroups that are infinite. Okay. So now what I want to do is talk about presentations of a group. To be really honest, this is notationally very convenient for describing groups, and algebraically it's a huge pain to work with presentations. So mostly we're going to use this as a notational convenience and not really show that like this is a presentation, this isn't a presentation. So what is a presentation? If we're in a group G, there are some equations satisfied by the elements of G. Those are called relations. So we have all these elements. There are various equations they satisfy. Those are the relations in G. And a presentation of G is a set of generators and relations such that any relation in G can be deduced from the ones that you've written down. So that's not a very helpful definition until you see some examples. So I'm going to pause and erase and show you some examples of presentations. Let's give some examples of presentations. A presentation for the group G is it is the group generated by A with no relations at all. So this is just a reflection of what we saw in the previous video, that in a cyclic group of infinite order, G to the K equals G to the L if and only if K equals L, that there are no relations. What about Z mod NZ? Well, it's generated by an element A, and the key relation is that A to the N equals 1. So I'm going to write 1 instead of the identity. That's a pretty standard thing to do. So what about Z mod NZ cross Z mod MZ? This is now generated by two elements, A and B, where A to the N is 1 and B to the M is 1, and those elements commute with each other. AB equals BA. So the thing here is that there are a lot of other equations in this group that are satisfied, and you just have to convince yourself that any other relation can be deduced from these three. So let me note that Z mod NZ cross Z mod MZ is cyclic sometimes. It's not always cyclic, but it's cyclic if and only if GCD of N and M equals 1. It's a good exercise to write out a full proof of this, but one sort of key idea is, what is the order of 1, 1? Like, what is the smallest number of times you need to add 1, 1 to itself to get 0, 0? Well, if that's 0, if that's the identity, then the number of times you added 1, 1 to itself must be divisible by N and by M. Okay, well, we don't just need to know the order of 1, 1, but what's the order of an arbitrary element? Like, how do you know whether or not there's an element of order n times m? Well, if you can compute the order of any element, that'll do it for you. Okay, so the last example that I want to talk about right now with presentations is the dihedral group of order 2n, d2n. So it's really convenient to write d2n this way. It's generated by r and s such that r to the n is the identity, s squared is the identity, and r times s equals s times r inverse. So r we're thinking of as our rotation. We can rotate our n-gon n different ways around. So you take like the smallest rotation, do it n times, you come back to where you started, and s is any reflection. So you should check that this matches up with your geometric intuition for like n equals 3 or 4, that rs equals sr inverse. Reflect and then rotate versus rotate and then reflect. Okay, so if n is bigger than 2, r is not equal to r inverse. So this is not abelian. I mean, r times s is just not equal to s times r, because if s times r equals r times s times r equals s times r inverse, and in a group you can cancel. If sr equals sr inverse, then r has to be equal to r inverse. So that's a quick way to see that this is not abelian. There are 2n elements in this group, r to the 0, r to the 1, up to r to the n minus 1, and then s times r to the 0, s times r to the 1, s times r to the n minus 1. So how do you show that this actually is a presentation for d2n? Well, you want to show that all of these elements are distinct, and that any word of finite length in r and s reduces to one of these 2n elements only using these relations that we have. So what's painful and annoying about presentations is that if I give you some generators and some relations, it's not totally clear that the group you're being given isn't just the trivial group. So Dummett and Foote give you an example of a presentation that looks kind of like this one, but in fact, you can show from the relations that they give that every element is equal to the identity element, that it's actually the trivial group. So this really is a presentation for D2n, and it's a nice compact way to describe the dihedral group, but you should not really expect to be tested on things like, here is a set of generators and relations, is it a presentation for this group that you know? Let's talk about a particular example of D6. So presentation is it's generated by R and S, where R cubed equals S squared equals 1, and RS equals SR inverse. So what do the subgroups of this group of 6 elements look like? Well, let's first look at all the cyclic ones. The cyclic subgroup generated by the identity is always the trivial subgroup. What is the cyclic subgroup generated by R? Well, it contains 1, R, and R squared, and then R cubed is back to 1. So it just cycles around. It's this subgroup of size 3. This is the same thing as the cyclic subgroup generated by R squared, because we get 1 R squared, and then R squared times R squared is R to the 4th, but R cubed is the identity, so that's just R. And then you multiply by R squared again, and you're back at the identity. The subgroup generated by S is 1 and S. S squared is 1. The subgroup generated by SR is 1 and SR. Why is that? Well, SR, SR, well, what is that? If I want to be really careful, let me use the associative law here and say that this is S times RS times R. I can move parentheses around in this way. And then RS, this is S times SR inverse times R. And now S squared is the identity. R inverse times R is the identity. This is just 1. So this element has order 2. SR squared also has order 2 for the same reason. So what about other subgroups? Well, one nice thing to note is if a subgroup contains a set A, it contains the whole subgroup generated by that set A. So it contains the subgroup generated by A. So what do we need to check? Well, if we have another subgroup and it contains some element, it contains the cyclic subgroup generated by that element. So it contains one of these. So we can go to each subgroup and add in some element that's not already in it. Like, let's take the subgroup generated by R. This has 1R, R squared. What about the smallest subgroup containing these 3 elements and also S? You can see that that's going to have to be D6. Same idea here. If you have like S, a subgroup that contains S contains 1 in S. Let's say, what if it also contains R? And then you're going to end up getting all of D6. Or what if it also contains S times R? Well, then it contains S times R, which is R, and you get all of D6. So in this way, in a really like exhaustive brute force kind of way, you can see that these are all the subgroups. So this is kind of a neat example because this is a group that's certainly not cyclic. It's not even abelian. But it is true that every subgroup, every proper subgroup, every subgroup except the whole group itself. So let me put proper in there. A group is always a subgroup of itself, but every proper subgroup that's actually strictly contained in D6 is cyclic. So that's an example of something that can happen.